It's a question number 30. The question goes like this. Imagine now you live in a 10-dimensional space. It's even more strain on your graphic chip. The question is, can we find 10 vectors in that 10-dimensional space? It's a part A of the question. The question says, can we find 10 vectors? I said n here, which is obviously a typo. Can we find 10 vectors such that if you compute the distances between any pair of those two, the distance will always come up with the same number, 5 root 2. It's this little symbol here. Do you know what the symbol means? It means for all. This symbol reads for all. It's another those symbols which sometimes abbreviates the writings. So if you never met this symbol before, it's the first time you met it, please welcome it. Anyway, so this line basically says to me, this line says that the distance between two vectors is always 5 root 2 for any or for all k's and n's not equal to each other. So any pair, as long as it's not identical vectors, deliver the same distance. Again, the source of our inspiration will be three-dimensional space, because that's the only space we know well, and that's the only space where we have some experience. All we have to do, we try to find some analogy and try to extrapolate this analogy to four-dimensional space. So let's just look at the three-dimensional space. Here it is. Can you tell me, actually I almost pictured the answer here, but it doesn't matter. No, actually I needed to, somehow I forgot to hide this, but it doesn't matter. Can you tell me please, in the three-dimensional space, can you name me 3 vectors? You see, I don't go 10, I just say 3 vectors. Three-dimensional space, 3 vectors. Can you name me 3 vectors which will have similar property? Any pair will be away from each other at the fixed distance 5 root 2 in three-dimensional space. 3 vectors such that any pair at the fixed distance from each other. Yeah, we have to take the vectors which goes along the axis of my three-dimensional space. Here they are. If you take any pair from these 3, there will be exactly by this distance away. And that's a simple Pythagoras theorem. Is if the length of the vector here is 5, then the diagonal of this, or hypotenuse of this right triangle, will be 5 times root 2. And that's the answer to this simplified version of this question, in case your dimension is 3. But now I think if I ask you what will happen in 10 dimensions, your answer will be immediate, isn't it? As long as you just refer to this experience with 3 dimensions, the answer to 10 dimensions goes straight away, isn't it? What will be the choice for the 10 dimensions? For these 10 vectors now. We choose first one like this. We choose second one like this. Obviously, we choose many others like this. I have a dots here somewhere. Yeah. We choose x3 in a similar fashion. We finalize our choosing with the 10th one, where the number 5 will be sitting in the last component. Each time, of course, we have a vectors which have 10 components. Each time we have vectors which have 10 components. And I think it's very obvious that the distance between any pair of these two will be always 5 root 2. And that's all there is to this example. The example comes with the letter H next to it, meaning that it's a harder question. The hardness of the question not in the computation. You have to, maybe by now you already realize that questions sometimes mark that they're harder not because they require some very long-going tedious computations. No, because they require some extra insight, some unexpected steps from you. For instance, here the main idea which made the solution possible is reference to the three-dimensional space and taking this as a prototype for our analyzing of 10-dimensional space. Good. Now the second part of that question goes like this. It says, is there 11th vector, 11th one? So on the top of this 10, which we chose already, is there 11th one, such that it will be again from at the same distance, 5 root 2 from the rest of the vectors. What should you do when you look at this part of the question? What would be your first step? Thank you very much. We have to raise the same question in 3 dimensions. All right, let's just look at 3 dimensions. Here's my 3 dimensions, something we can imagine very well without any graphic chips or whatever, right? We got 3 vectors here, each at this distance away from each other. Here's a question to you. Do we have a fourth one? Fourth one, not 11th. Fourth one, which at the distance 5√2 from the other 3. And if we do, how many of those we have? Any suggestions? Yes, please. 555. I disagree with the numbers. I don't think it will be 555, but you sort of hinting to the fact that if you take the line through the origin, and if you run it through the middle of this triangle, it's an equilateral triangle. It has a center point, the point of the center of the circumscribed circle or inscribed circle. It's the same point. If you take this line here, and I can't picture this here, but I'm relying on your imagination. If you take this line, if you run through the origin, if you run this line through the origin and through the center of this triangle, it will be a perpendicular line to the plane of this triangle. Every point on that line will be equidistant from the vertices of this triangle. Do you agree with me? It's that's something you say it's obvious because it's your experience with 3-dimensional space. If you have an equilateral triangle sitting on the plane, if you raise a perpendicular from the center of that triangle, every point on this perpendicular will be equidistant to the vertices of this triangle. All we have to do, we have to choose the one particular point which will be at the given distance 5√2. Yes, please. -5/3. You did the computation already. Thank you. I didn't do the computations here on the slide for the 3 dimensions. I did some hints of the computation for the 10th dimension, but thanks, it's quick. So all we have to do, we have to choose this point on this perpendicular, which will be of our preset distance. In fact, remember I asked you if we do how many points we have. How many points on this perpendicular will be at this preset distance from the vertices of my equilateral triangle? In 3 dimensions, yes. 2. One will be above the plane and the other one will be under the plane. Now, if again, you see, after we analyze things in 3 dimensions, we can take this to 10 dimensions. If we try to repeat the same strategy for the 10 dimensions, all we have to do, we have to look for the 11th point. Yeah. All we have to do, we have to look for the 11th point of this structure. Because this perpendicular I was talking about, it's the perfect bisector. It's the one which has all identical coordinates. We don't know the value of that coordinate. We can find that value by computation. Some of us have done it already, well, for 3 dimensions. But in principle, that's what we're looking for. We're looking for the 11th point of this structure. This x1 repeated 10 times. And I think it's very easy now how to, well, I mean, the way to find this x, actually, all we have to do, we have to take this point, we have to subtract from one of these points, no matter which one, and equate this to the preset distance like this. Do I have it somewhere here? Yeah, here it is. If I compute if I take the difference between the vectors x11 and any other vector, you see I just name it x sub k, because it doesn't matter which one I take, what will happen is this. For every component in your x sub k vector, which is 0, you will have just x here, and you will have this x 9 times. And for this one single component where you will have 5, you will have a bracket like this when you compute the distance. And now all you have to do, you have to equate this. You have to equate this to this number. You have to equate this to the number 5 square root 2. Well, if you do that, if you equate this to this number, let's say you will come up with a simple quadratic equation. You can square both sides. If you square both sides, that's what you will come up with. If you expand the brackets, that's the expansion. You can join this 9x squared with this x squared. You can take this 50 on the left-hand side. Eventually, you will come up with a quadratic equation like this, which we all know how to solve, I hope. Do I have a solution for this? So the system can help me to solve it, but you don't have to rely on this. In fact, I encourage you to solve that. Just for the matter of finite presentation, I can solve for x. These are two solutions of my quadratic equation. I'll put here dots indicating that these dots are hiding the method of solving of quadratic equation, which is not officially part of this topic. I hope that you know this method. In the first year, and that's certainly my fault, you can blame it on me. In the first year, we adhere to the notation when we use single vertical lines on the side of the vectors. Single vertical lines. So when you see these double lines, when you see a double lines, you should just identify this with single lines. I was preparing this yesterday, and I was like under the influence of the other topic I taught, and that's a higher honors topic, and in that topic we use double lines, and that influence actually ruined the whole thing right now, you see. I hope you're with me. So if you ever see this again, in my presentations, you just immediately replace double lines with the single lines, and we all know what the single lines mean, right?